Thank you, Anna, for that very nice introduction, for inviting me to be here. It's an absolute pleasure, and I love the name of the conference, the title of the conference, because a lot of what we do in this project really is about conversations between humans and data, conversations between humans and the computer, conversations between multiple humans. Let's see how well this works. Maybe not. Yes. So I don't need to explain to this audience that we're all drowning in data, regardless of your domain, regardless of your discipline. Pretty much every field of human endeavor today is becoming a data-intensive one. From traditional areas like the physical sciences that have had massive amounts of data and computation to social sciences, all the way down to individual personalized data that you may be collecting at home on medical devices, for example. So we're all drowning in data. But there's one thing that does remain sort of limited and constant, which is the size of the meat, the bag of meat that's in here. That's not getting any bigger. It doesn't matter how big how large our computers get. It doesn't matter. This isn't working. It doesn't matter really whether you're doing analysis on your trusty old little laptop or you're using one of the big supercomputers like this machine, which is just up the hill, where Anna mentioned that I also work at Lawrence Berkeley National Lab. Your brain isn't getting any bigger. And so how do we build machinery that allows you, as an individual who still hopefully is the one responsible for asking the relevant questions and for making the important decisions, regardless of how much AI we end up having and many of you end up developing. I hope we don't abdicate those two critical responsibilities. How do we build tooling that helps us bridge this divide? And this is sort of where IPython and Jupyter try to sit. They try to sit as an interface between the humans in thinking and reasoning and the computers as tools. As Anna mentioned, all of this began back in 2001. I was a PhD student in physics in Colorado. I was working in a rather obscure subfield of physics called lattice QCD, and obviously faced with A, cranking on my dissertation, B, playing with code. That was an easy choice. And so I disappeared from my advisor's radar for a few weeks, and with a very good excuse. I was going to make a tool that was going to make it easier to do my work more efficiently, right? That's always the argument we make. I said I'd be gone for an afternoon. It's been 16 years and I haven't come back, so never trust me when I give you a time estimate. That's the size of my error bars. 4 hours plus or minus 20 years. But IPython was born with a very specific kind of workflow in mind, which is Python was a programming language that I learned about. I picked it up. It seemed like fun. It actually was it had a very clean syntax. But the one thing that was important for me as a scientist was that I wasn't writing software. I was actually looking at data. I needed to run a little bit of code, pop up a plot, look at a library, maybe open a data file. And based on what I saw on a plot, based on the result of running a small amount of code, the next step would change, right? So it is very much a conversation. It is very much a dialogue. There's no predefined set of constraints and requirements given maybe from another department that says, build this. It is, here's the tools, here's the data, here are the questions. You think your way through. And what Python offered for that was a little bit limited. And so IPython was basically built to give me the tools to do all of that interactively and in a very exploratory manner. Now, it's very important at this point to make sure that I clarify that all the credit for everything you're going to see does not go to me. It's really a huge team effort. This is a project. These are images from our two last developer meetings, one at LBNL and one here on campus, just across the street, actually. And we have a very diverse team of people who come from academia, people who come from industry. This has all been built by basically students, researchers, academics, and company folks who feel that they can build better tools for their needs. Rather than simply waiting for somebody else to create them, we can build our own stack, because it's not just IPython and Jupyter, it's the entire open source ecosystem that is accessed through these tools. IPython and Jupyter by themselves are just gateways into an entire systems for analyzing data, data visualization, summarization, algorithms, machine learning, etc. And so this large collaborative effort, skipping about 15 years of history, we ended up releasing around 2011 the very first version of what at the time was called the IPython notebook, which many of you have probably used. Just to summarize, the first approximation, it's sort of like a word processor with a brain, if you will, right? It's an environment that allows you to have documents, it allows you to have natural language, it allows you to have mathematical equations, but you can also include code and the output of that code, which can all be live in the same document, and it is accessed through a web browser, which turns out to be actually really important because it allows us to deploy the exact same experience whether you're running locally on a laptop, you can run a web server on a laptop, or whether you're running that remotely. And that has proven to have many, many benefits because it makes it very, very easy to basically put the computation right where the data is, in the cloud, in the remote environment, in the remote server, and the experience is exactly the same as the one that you would have working locally. Now, to give a little bit of kind of an abstract model of how we think about this, I think it's useful to look at how the web is structured. So if we think about the web is based to first order, and this is not a technical low-level description of the protocol stack, but kind of conceptually, I think of two important pieces of the web. There's the HTTP protocol, which acts, it's a transport protocol, stands for Hypertext Transport Protocol, and it allows clients and servers to speak. Now, even though it is called a Hypertext Transport Protocol, and most of us interact with HTTP servers via web browsers, you don't have to use a web browser, right? It's perfectly possible to build HTTP-based services where you connect with a variety of clients. And so the underlying protocol, even though it's largely driven by the constraints and the needs, and the original design was driven by the desire to build the web, the World Wide Web and HTML, the underlying abstract transport machinery can be repurposed to design many other services. And if you do want to put a browser in front and display information for a human, the traffic of that protocol can be captured, encoded, and rendered into HTML and web pages that are consumed for the human. So these are sort of the two basic building blocks. And so similarly in Jupyter, you can think of our protocol as kind of our moral equivalent of HTTP, if you will. We actually went out and defined a proper protocol where we said, okay, when we're working interactively in IPython at the command line, what is it that we do? What are the many actions that happen in that process? What happens in that dialogue between the computer and the human? What happens? You send code to execute, you get error messages, you get results, you may query objects, you may query libraries, you may send control messages to control the flow of execution. All those things were encoded in a very specific set of message types, message responses, and a topology for the connections of how clients and servers need to connect to one another. And we formalize that into a description that uses a specific library for the networking called 0MQ. It's a simple, lightweight C++ library that has basically no dependencies other than a C++ compiler, and it has proven to be a lovely tool because it's extremely efficient and fast, and it's available, bindings for it are available for virtually any programming language you can think of. So having this little core, basically, if you have 0MQ, you have half of the puzzle, and then we encode all the data that goes back and forth as JSON packets. So basically, if you want to speak this protocol, you need two things. You need to have bindings to 0MQ, which virtually every language has, and you need to have a JSON encoder and decoder library, which these days basically also every language has that. The choice of JSON was partly because, well, we were going to be rendering this mostly through the web, and it's kind of the lingua franca of the web browsers. And then similarly, on the receiving end, if you decide that you want to build a document with this, then we do have a document format. And the document format is effectively the JSON packets stitched together with a bunch of metadata around them to tell you a little bit more about what happened. But basically, each of these things goes into a JSON blob that gets transported over this, and they get assembled into a document that we can then render. We can render it on a web browser, but we can also do many other things with it, as we'll see in a moment. So the actual protocol tries to capture everything that we do when we do computation interactively. So it's basically the old-fashioned Unix REPL, the read, eval, print loop, the thing that happens in a shell where you type some code, it takes your input and it prints your output. We kind of took that idea and put it sort of on modern web-based steroids, so that you would have not only the display of printed output like text, but you could say, oh, my output object is a figure, and that is a valid display output in any format that a browser can display. We made mathematical output a first-class citizen, so that you could actually compute something whose output is mathematical notation in LaTeX, and it would be properly rendered. But we said, since we are in the web, even though we do want to be able to target other output formats, we sort of made the web a first-class citizen and the driver of the design, of most of the design constraints. It meant that you could have arbitrary HTML and JavaScript output, which means that objects can display themselves in any visually meaningful and sophisticated way that you want, and you can even have live JavaScript that can lead to things like interactive widgets. So this is an example of putting with one of our libraries a little decorator on a function, and you automatically, without writing any more code, that is the output of that code, you automatically get a slider that makes this function interactive over the variable n, and as you slide it, the function we execute, in this case, it's expanding a polynomial. And so it's actually doing a symbolic computation as you slide it. The point is, these are all the actual representations of the outputs of the protocol. And those building blocks make it possible to represent things for a wide variety of languages. The project began, as Anna mentioned, as IPython. It was an interactive environment for Python. We gradually kind of abstracted that into a full-blown protocol that had multiple clients. In fact, before the notebook, we had a different client called the Qt console, which was a sort of like a terminal-based environment, but with rich graphics. It was kind of an in-between between the classical text-based terminal and a full-blown notebook. It was a stepping stone to that. But once we realized we had all this architecture, it became very obvious to say, well, the programming language, that could be a parameter too, right? Once you've abstracted enough, one more thing that to parameterize can be the programming language. And so it was very easy to say, oh, we could use the exact same protocol with another programming language, say Julia. And so we spent some time with the authors of the Julia programming language, who here uses Julia, by the way, just out of curiosity. Is anyone here using Julia? One person. Okay, so it's a new tool. It's a new tool that came out of MIT. It's been out for a few years. It was very much born in the world of applied mathematics. It came out of Alan Edelman's group, but I think it's a tool that will probably begin appearing on your radars depending on which industries you end up working into. People in econometrics and finance are starting to make a lot of use of it. It's also a high-level language, very much in the spirit of Python and MATLAB, but designed with modern ideas about compilers and runtime systems. We also added R support to it, so one of my postdocs wrote the first version of the backend that would run in the same notebook environment, pure R code instead of Python. And the point is, these were implemented natively by those teams in those programming languages. It's not a big blob of Python somehow communicating in some hackish way with a Julia process or an R process. It's actually an R process directly encoding the protocol and sending the JSON packets back and forth. And once a couple were done, I like to say that in kind of systems design, n equals 2 is a lot closer to n equals infinity than to n equals 1. Because typically what happens is, going from the first to the second is when you have to break down all of the hidden assumptions that you made about the original system. And that's exactly what happened. As we went through the process, the Julia people told us, oh, the protocol is missing this, or you encoded this bit of information that is really very Python specific. There was an undergraduate student down in Southern California who was building a lovely Haskell kernel, and he gave us a ton of feedback on things that really were not appropriate for the Haskell kernel that we had put into the protocol. And by baking that out with a couple, eventually we ended up with a system where now I think there's over 90 different kernels implemented for this. Some of them are kind of afternoon toy projects. Some of them are just a lot of proof of concepts. Others are actually production systems that people do use as an everyday tool. And this idea of building this environment that would be very generic actually had an overriding goal, which is that as much as I love Python, I've been involved with the scientific Python community now for 17 years or so, Python is not what matters. Technology is not what matters. Scientific knowledge, research, education, communication, those are the things that we're after. And very specifically, a vision of problems with scientific research that in my mind was extremely well articulated already 20 years ago, well before I started working on any of this, by David Donahoe. David Donahoe is a statistician. He's faculty at Stanford. And back in '95, he wrote this statement as part of a document about reproducibility in computational research. He's faculty in statistics, but he's kind of one of these people who lives at the intersection between applied mathematics, signal processing, and statistics. And as part of the manual, actually, for Wavelab, which was a package for wavelets-based signal processing written in MATLAB, he wrote this, which honestly I believe is one of the most concise and clear statements of why we should make our research reproducible, because it is really true that today, if you don't give someone the actual code, data, and environment behind a scientific result, it's near nigh impossible that simply from reading the methods section of your paper, they'll be able to replicate it. And I am as guilty of that as any, because I've published papers where I know that without our code, there's no way in hell anyone is going to replicate that, because it simply would be too much work. And so what we've tried to do is provide some tools that can help in this direction. I want to highlight this particular example simply because it's very fresh in my mind, and it illustrates something very nicely in the connection, in the value that these things have all the way down to students. So this is an example of a paper that was published recently it's a statistical analysis of wind data from Europe, done by two geophysicists from Norway. They published it in a journal from the Royal Society. But that's what David Donahoe would call the advertisement. The paper is the advertisement, right? That's the sales brochure, the glossy brochure. The real work is that the authors actually put out a GitHub repository, and this GitHub repository contains their code and the analysis notebooks that create the figures. So this is the PDF of the paper. If you go to the website, it's an open access paper, so anyone can download it. This is the actual PDF that you could print. This is the notebook on GitHub that anyone can access, and which has, as you can see, the exact same figures that the authors published. So you can actually replicate, in principle, you can replicate every result. In principle. So, but the beauty of this is by making it open. So right now I'm teaching a course called Stat 159-59, Reproducible and Collaborative Data Science. It's listed as a statistics course, but it's actually open to students from any department. I have about 60 students, and I have a very interesting mix of students from all over the campus. And one of the projects that the students have been working on this semester was actually trying to replicate those results. The authors, it's an open science journal. They make their data available. They make their code available. Well, can you? And so they tried, and most of them succeeded because, in fact, they could, but not without some extra work. But part of the beauty of it is that as part of the process, we discovered a weird little glitch regarding the creation of some of the figures. That actually was a subtle incompatibility. I wouldn't call it exactly a bug, but it was a subtle incompatibility that had appeared in some versions of the visualization library that we're using between the publication of the paper and today. And this led to the lead developer of matplotlib, which is the plotting library that probably many of you use if you use Python, actually filing a bug 2 weeks ago, filing a pull request with the author of the paper on correcting this specific incompatibility that was now making the figures appear wrong. I gave the author a little bit more context so he would understand, like, why in the world are people making a pull request on my 2-year-old paper out of the blue with this really bizarre matplotlib 1.50, 1.51 incompatibility, and by the guy who currently leads matplotlib itself, which seems very odd thing to do. So I gave him a little bit of context, and he very, very kindly responded, "This is great, thank you very much." So I think this is an example, and obviously the students were thrilled to see this, because I told them this is thanks to the fact that the students are diving into this, that we can come back to you and actually improve this work. He was extremely gracious, and I think it's a great illustration of kind of the virtuous cycle of open communication and open dialogue around code and data that these ideas enable. And today, this has grown actually into now infrastructure that we're building. So this is a project that called the Binder project is a project that was started by Jeremy Freeman and an engineer in his lab, Andrew Osheroff, a couple of years ago. Back when Jeremy was at the Howard Hughes Medical Institute, he's a neuroscientist. He was doing absolutely mind-bending work on analysis of real-time neural data from zebrafish, but he recently actually moved to the Bay Area. He closed down his lab, and he's now working with the Chan Zuckerberg Initiative, actually on open science and tools for computational biology and biomedical research that are open. And Jeremy and Andrew, after a conversation we had, started building a project that was effectively, in my mind, sort of the last step in the embodiment, in the physical or computational embodiment of David Donahoe's idea, which was the Binder. The Binder is something that allows you to put the URL to a GitHub repository here. And as long as you have a GitHub repository of notebooks, very much like the one I just showed you from Ben Lacken and his co-author, that has the right structure and that declares what dependencies your code needs. So you have a repository, and if you tell the system with a simple file, just you follow a convention so that the system knows what are your library dependencies, and that can be done in the, if you want the technical details, it can be either an environment file or a full-blown Docker file. Then you click on one button, you click submit, and the system goes out and builds a Docker container that contains the entire the binder, right? You have the sales brochure in front, but you get the full binder. There it is, with code, with data, and the Docker container is ready to go, and it's actually live. That link is a live executable link, so that you can share a live Docker container with anyone. We just got a grant from the Moore Foundation, actually, to continue the development of this, because there are people here at Berkeley. This was a prototype. It was very successful, but it kind of died under the weight of its own success. And so now a teams here at Berkeley, down at Cal Poly, and at Simula Research Lab in Norway, we got together and have kind of re-engineered this prototype into hopefully a more stable and long-term solution that we hope will be adopted by scientific publishers to actually change the publication model. And this brings me to a very relevant and for me very meaningful scientific event. Some of you may have seen in the news that this is a screenshot from the UC Berkeley physics website from last week, that this year's Nobel Prize in Physics was awarded to the LIGO collaboration. One of them was actually a UC Berkeley alum, which I didn't know until last night when I read this, for the discovery of gravitational waves. So for those of you who may not have seen this, a quick reminder, gravitational waves were a prediction made by Einstein, who predicted that in the event that in the universe large masses, large bodies of matter move under acceleration, they will actually radiate energy, and that energy will be radiated in the form of waves that travel very similarly to how electromagnetic waves travel, light, like this. But those waves, while this is a wave where the electric and magnetic fields that exist in space oscillate, that one, the wave that travels when large masses move around, is a wave of space-time itself, which means space and time themselves distort and stretch. That was a theoretical prediction coming from this particular equation, the field equations for space-time, that is very, very tricky to detect. It turns out that what you have to do is you have to find distortions in space-time that are absolutely minute. How small? 1 part in 10 to the 21. If you think about it, that's crazy, actually. The notion that you can do that is insane. To give you an idea in terms of sort of images, imagine that you're looking for an object of the size of, say, roughly a person, like 1 meter, size, human-sized, 1 meter size. But the image, 10 to the 21 meters, would be an image which is not the size of a city, not the size of a planet, not the size of a solar system, but the size of the whole Milky Way galaxy. So you're looking for one person in the Milky Way. That's what 21 orders of magnitude of sensitivity is. They worked for about 40 years on this, and what they did was they built 2 instruments, 2 interferometers. These are 4-kilometer long, straight, high vacuum tubes where you shine a laser like this down each end, and the light bounces back and comes in at the middle, and in the midpoint you analyze it, and what happens is if a gravitational wave comes through, the whole thing stretches a little bit differentially, right? As the wave goes by, one of the arms will stretch a little bit more, the one a little bit less, and that little wiggle will be detected as an interference pattern as the light bounces back between the 2 of them in the middle. And the trick is you want to put 2 of them, at least 2, if not more, and actually now there's a 3rd one in Italy. At the beginning there were 2, so that you can be sensitive to spurious noise, because the problem is precisely with this crazy sensitivity problem, basically anything will be bigger than the signal you're looking for. Somebody sneezes down the hallway, a truck drives by 5 miles away. The motion of the moons of Jupiter around the planet Jupiter produce a bigger gravitational signal than what you're looking for. And so having 2 of them allows you to do a very sophisticated amount of data analysis to detect the coincidence and extract what's real from what's not. And so in September 14, 2015, a huge event was detected. It was the merger of 2 black holes coming in through, that arrived right as the instrument was about to come online. And this is an image of the paper where they published this. And first of all, this image, for those of you who do Python, you probably will recognize it. You'll kind of see, you get used to recognizing, oh, that looks like a Matplotlib figure. And so for us, it was enormously, enormously rewarding to see that one of these results that we knew was going to be one of the most significant scientific results of the decade, if not the century, had been done completely with open source tools. And furthermore, the LIGO collaboration actually posted their data analysis in the form of Jupyter notebooks that they put out online with all of their data. So if you go to the LIGO Open Science Center, you can actually download and run and listen to the sound that these things make. I don't know if... Did you hear that? Whoop! So that is the sound. That rise in frequency is this. This is a spectrogram of the signal. That is exactly slightly frequency shifted so that it's a little bit easier for humans to hear. But that is the actual sonification. Let's not call it a sound because we don't exactly hear it. But it's the actual sonification of two black holes merging 1.3 billion light years away, represented as a sound object in a Jupyter notebook. But this was not done by us. This was done by the LIGO Center. And now, in their by the LIGO collaboration, and in their Open Science Center, they actually publish, for every new event, they actually publish not only the notebooks for you to view, but the actual binders for you, so that you can go, click on that, and actually play with the data, run the analysis, listen to the results, visualize, etc. So for us, this is kind of a validation that this idea from David Donahoe from over 20 years ago is now a technical reality, and now we need to do the social and human work of adopting this. Now they now continue to do this. So as they get new results, because they've been seeing new events of different characteristics, the most recent one was just a few weeks ago, which was the merger of two neutron stars, and that one was seen by 3 detectors, so it was better localized spatially. They continue making their data releases, and it's not only papers that are done this way, it's also books. So now we're seeing a growing collection of books around data science that are actually being published either as collections of Jupyter notebooks or with collections of Jupyter notebooks, depending on how the authors create the materials. These are books that are accompanied by executable materials so that you can trust that the book you're reading, the figures in the book you're reading, that you don't have to wonder, well, did the author actually copy-paste the right version? Did they maybe update the scripts after they put it and they left an old one? Is the version of the script that they copy-pasted the right one that actually runs with it? No, none of that nonsense. Everything was created by actually running and executing this code. You know that figure comes from that input, and that can be rendered live. And most of these authors have actually made the collections of notebooks that accompany their books available on GitHub for you to download. And this brings me to a topic that I'd like to kind of put open for conversation because in an audience like this, which is how can this help and modify our practices around communication in academia and the communication of scholarly ideas? Because I think that over time we've perverted the role of scientific communication and scholarly communication by conflating two things that originally were separate. So originally, the scientific literature served the purpose of communicating ideas, of sharing with others what you had done so that others could understand it, validate it, work off of it, and build new ideas off of it. But along the way, science became a large-scale professional enterprise, right? And scientific publication became the way of measuring that activity, or the way of measuring and counting that activity, and ultimately building professional credit and career. And I think these two things ought to be distinct, because what we've done is we've created a system where humans have no time to actually read the body of literature. I don't know if anyone here keeps up with the literature in their field. I want to talk to you because I have no idea how you do it. I know that no matter what I do, I'll be perennially behind any topic that interests me. And so I think the only reasonable outcome, if we want a healthier system for this, is to accept the fact that in the future, most of the literature will need to be read by machines. And so maybe we should be building our literature in a way that is more friendly to the machines and take this as an opportunity. And so that's part of the reason why we designed the Jupyter Notebook as this JSON-based data structure, because it is a very machine-friendly entity. It's something where you can store a lot of metadata about what happened. You know what is the difference between natural language and computational language. You know that this particular output is connected with this particular input. You can do a lot more sophisticated analysis of this. You can still produce a PDF. You can still produce a book. You can still produce a web page if that is where the human wants to consume it. But the machines can do the more intelligent consumption at the first layer. And what I would like to see, and what I would hope this could lead to, is a future where, in a sense, we publish less so we can actually read more. Because a lot of that time, by the way, in publishing all that literature that no one is reading is wasted time in peer review and in a lot of effort that really, I think, is unnecessary. And I could imagine a future where more of our everyday work is captured in a way that allows for proper credit, for proper dissemination, for proper use by machines, and we publish long-form detailed articles that merit peer review, that merit in-depth analysis on a less frequent basis. And I think that would be a healthier setup for everyone involved. So maybe some of you will make some progress on this topic. And to start wrapping up so that we have a little bit of time for questions, I want to flag that all of what I've talked about is the use of these tools, as a single user on your laptop or on a remote machine, but as a person, as an individual. But the project also has an encompassing piece of infrastructure called Jupyter Hub that allows you to deploy Jupyter in a large environment, in a group, in an organization. And this is now being used, for example, at UC Berkeley. We have this lovely course called Data 8, or Foundations of Data Science, that was designed a few years ago, targeting freshmen, incoming undergraduates, with the idea that an educated citizen of 2020 ought to be someone who, regardless of their major, regardless of their discipline, ought to be someone who is capable of reasoning about data in an intelligent way, and in an educated way, because data will impact their life. Data will impact political decisions that affect them. Data will impact healthcare decisions that affect them. And so having a reasonable level of inferential literacy was an important goal. And so campus designed a course called Foundations of Data Science. The textbook is an open book on GitHub. But when you go to read the chapters of the book, each chapter has this little interact button that takes you to a hosted version of a Jupyter notebook so that the students can access it. And by having this technology deployed, this has become the fastest growing course in the history of UC Berkeley. This was a picture from a few weeks ago, the first day of the fall session. It had about 1,200 students. This is Wheeler Hall. I think it's the biggest lecture hall on campus, right? And it was basically standing room only, packed to the walls, and not all the students actually fit. The capacity of the room is like 750. So there's about 300, 400 students who, 300 to 400 students who have to watch the lectures online via video and work online. But the point is, this is making it possible to, by having a combination of everything being open source and all of the machinery being deployable, it has made it possible to offer this kind of modern educational environments to our students here. And finally, I did want to flag a little bit about a topic that I imagine is relevant to many of you, which is the role of data in society in terms of communicating with society when it's not the specialized scholarly literature. This is an example of an article that was published by 538 about gender disparities in Hollywood back in 2014. And they published a lovely analysis of this data, but they didn't publish their data. And so Brian Keegan, who's faculty at the University of Colorado's equivalent of the iSchool, published this lovely analysis in a Jupyter notebook calling 538 out for not being open about their data. He basically reconstructed the analysis by trying to figure out what they had done and published this epic notebook with much more analytical detail than they did. And to their credit, they actually responded in a great way, and they said, yes, he made a very important point. 538 and similar sites should make their data available, and we couldn't agree more. And boom, they put all their data now up on GitHub in the form of a combination. I think they're mostly using our scripts, but the point was not that it had to be in Jupyter Notebooks, is that they had to make their code and data available. And now this seems to be picking up momentum. This is an example later of an LA Times article about crime in LA. And this was one of the authors, Anthony Pesci, one of the authors of this particular article in the LA Times. And if you look at the GitHub ID, this article actually came with this one. They came straight up with GitHub data, and this is the author. One of the journalists who was in the piece is the author of the commits for these notebooks up on GitHub. And finally, this is being adopted as an industry platform. So we have a very good collaboration with industry. Most of the large cloud providers now have, in one form or another, products that are based on this technology. And now we're kind of at the point, as Anno mentioned, of beginning to grow this into a community where we try to actually have a healthy intersection between researchers, academics, educators, government scientists, and industry participants and industry developers. These are some images from our first Jupyter conference, which was in New York a few weeks ago. It was very stressful. I had never done something like this. We did it with O'Reilly Media, but it was a great success. It was a lot of fun. We had about 700 attendees. We sponsored a bunch of students with NonFocus, the nonprofit foundation that is kind of the umbrella for Jupyter, who attended. And we're going to have it again in 2018. So I'd love to see some of you at the conference. Thank you very much. And hopefully we'll have a few minutes for questions.
Fernando, thanks so much. We have about 10 minutes for questions. We've got a couple of mics roving around the room. So if anyone wants to kick us off, Mark, why don't we go there, and then we'll come, Jennifer, to you.
Is it working? Oh, it is. Hello. Great presentation. Thank you very much. I was really curious about your notion that the books, the publications that are going out now are accompanied by code that actually adds depth, adds data, produces a 3D view of the presentations, the material presented in the publication. Can you tell us a little bit more about your view, your vision, what you see in the future about how this might actually develop? The LA article about the underreporting by the LAPD was a great example, but that goes into data, and that presumes that people are data savvy, which right now I think, a greater percentage of the population we hope will become more data savvy, but right now that may not be the case. So where do you see this going for people who perhaps may not be as data savvy in the future?
So I think in my mind there's kind of two sides to that question. I'll try to briefly address both. One is on the specifics of the journalism and data. It's true that today we can't expect the vast majority of the newspaper readers to be statistically sophisticated enough or to have the time and the interest in doing that. For me, part of the importance of that is that it is possible. Even if only a tiny fraction of the audience does go and check on that, the fact that the data and the code are available introduces an element of transparency, of trust, that even if I am not going to do that analysis, the fact that it's possible for someone to do it gives me a measure of confidence that it's more likely than not. It's not a guarantee, it's not a proof, but in my mind, it's an element it suggests, or it provides supporting evidence for me that those results and that data is probably more trustworthy. Because if it's a complete mishmash of nonsense, but they did make it available, that will probably be found out quickly, right? So it's very similar to the notion of trust in security code being done by open analysis of the protocols, and why it's important that security protocols, for example, NIST actually publishes all of the protocols are subject, that are the standards in security, are subject to in-depth analysis by the cryptography community. I'm not necessarily a specialist, and I certainly don't have the expertise to analyze cryptography code, but it gives me an element of trust to know that it was made available to those who do have that expertise. So that's kind of one direction. Hopefully, with changes in education, like the work that is being done at the iSchool, the work that is being done here at Berkeley, that baseline will also improve. But that in my mind is one way in which it helps. The second one is on the scholarly communication side. What we're hoping is with projects like Binder is to actually bring this to the publishers. And we've already had interest from publishers, academic publishers, that actually to make this the standard. Imagine if you're a peer reviewer for a paper, wouldn't it be much nicer if instead of a PDF, you get a PDF and a clickable link where you can actually run the code immediately without any effort, without installing anything, right? Because chances are you won't have the time to build all that stuff, and you wouldn't do it. Peer review is an unpaid volunteer labor as it is, so you probably aren't going to invest days and days trying to debug their code. But if you could click on something and run it, and maybe tweak a parameter, maybe say, my data is kind of like theirs. Let me drop my data and see if their method is really as trustworthy as they claim by putting my data, and it only takes me 10 seconds to just drop a file and rerun it. Then that would also raise the bar in terms of the quality of the communication around code and data. So these are a couple of directions where I hope this can help.
Great, thank you. Jennifer.
Hi, one of the things that you talked about earlier was the conflation of the reproducibility and also credit. Do you envision a time when machines can help people trace intellectual contributions?
Yes, certainly that's part of my thinking with tools like this, is that you could imagine capturing a lot of the more everyday work in this form, where you have both, basically these are kind of the modern equivalent of lab notebooks for computational research. That kind of work could be made available in a more rapid fire fashion. We can still have, I mean, all of this is version controlled. For all of this, we have hash identifiers, you can have tags, we can have DOIs to make it citable. We can access the data underneath it and cite the data as well. And if that trail of credit is made available for the more everyday work that probably doesn't need extensive peer review, because in fact, that peer review is leading to no reading anyway, right? So we could make it available, still track its impact, right? And then have the peer review, the more traditional methods of peer review and kind of analysis reserved to smaller volumes of the population. Because for all of this, it could, and in fact, there are already companies, the Chen Zuckerberg Initiative purchased a company, they're called Meta. It was a Canadian startup that basically has been ingesting a lot of the scientific literature in brute form PDF, right? So the ingest is a complicated and messy affair, but they've been trying to ingest the literature to establish the knowledge and semantic and connection graphs of the entire body of scientific literature, not just citations, but actually building semantic knowledge. If these were the methods of publishing, I would imagine that work could be done more easily, more transparently, and we would also lower the burden of the scientific community on what I think is unnecessary sort of bookkeeping and accounting.
Thanks. Other questions? Anyone else? Pick up. Yes, sir. There's a mic coming to you there. Thank you.
Hey, thanks for the presentation. Just quickly, maybe the issue of version control will become more important with the reproducible research and the notebooks and the binders, I guess. So I think you get asked this a lot, like the notebooks are not very friendly with version control, the JSONs themselves. So I think if I understand correctly, Jupyter Lab is trying to address this. Can you quickly tell us what's the future of that?
I think I may have that slide here. So your question is about this, which is miserable, right? This is absolutely all, yeah, I guess asked enough that I do have a slide for it. This is absolutely miserable. This is looking at the diff of a JSON data structure at the command line, and this is horrible. It's not quite Jupyter Lab. It's actually a separate project that can be used already and independent of Jupyter Lab. We're hoping to integrate it more nicely into Jupyter Lab, but it's a project called nbdime, which is short for Notebook Diff and Merge. So it's basically a diffing tool that understands the semantic structure of a notebook and understands that it is a data structure where when you're doing diffing, you actually want to look at, oh, this is a cell and this is the code that changed in the cell. Oh, this is a text cell and this is what changed in the text cell. Or, oh, there was a figure here and now the figure looks a little bit different. And so this is a tool that is already available, nbdime, you can pip install it, and it tries to address that very problem with kind of a more civilized interface.
Right. Any other questions for now? Got one, yeah, just right in front there of the previous questioner. Thank you.
Hi. While you've been developing this, have there been any intuitions you have had about users or the deploy of it that have been wrong? Like, what have been some dead ends you may have gone on while developing this? Or has it been perfect?
No. It's got an interminable list of problems. One of the most surprising ones, I would say, is it's something that I sort of knew, but it never bothered me, and it has become a persistent complaint. And it's not really specific, by the way, we're not claiming to have invented this notebook concept. This notebooks existed in Mathematica and Maple well before IPython and Jupyter came along. And in fact, I was a heavy Mathematica user myself when I was in grad school. And notebooks have this peculiarity where you have a document, but the way the document looks on the screen does not necessarily reflect the state of the underlying computational system, right? Because what happens is that computational engine is the result of all the actions that have been taken on it. You ran this code, and then you ran that code, and then you created this variable, and then you deleted that variable, and so on and so forth, right? But on the document, you could have done those things out of order. You could have moved cells around. And the weird thing is, many of us who came from the Mathematica world, most of the original authors of IPython were physicists. We used that a lot. For some reason, we got used to that, and it didn't bother us. It is a constant source of complaint and pain, especially in education. It really creates a huge amount of tension between kind of the learning that is focused on this and this weird thing that happens that completely throws for a loop, especially students at the beginning. And it's something for which none of these systems has really a very clean solution yet. We're beginning to kind of imagine ways in which the user interface could help, and there's a few very, very band-aidy mitigating tools that we have. We can restart and run them all quickly with a single menu button entry, but it doesn't completely assist the mental disconnect that exists for a person between the abstract model of the computational process and the visual representation that they have in front of them. And that gap has been much more painful and much worse than I had ever expected it to be, and harder to solve as well.
Couldn't you just like highlight, like put a border in red around anything that's out of date because of lower things that have been communicated?
That's one possibility. We need to begin experimenting with simple things and testing, actually doing some honest-to-God user testing to see what helps and what doesn't help. There's been attempt. You could imagine also doing analysis, actually dependency analysis of the code, because sometimes it's not just out of order. Some things don't actually depend on the previous one. So it's a quickly diverging mess of rabbit holes that has made this problem kind of difficult to tackle. But yes, that's certainly a valid idea that we can and we should try.
We've got time for one more question, so let's, okay, the mic is there, maybe two. Okay, I'll come to you, Tiffany. Yes, sir.
So,
I'll be brief.
Based on what you just said, when you look at data, it's really a state machine. So when you do an operation on the data, it changes the state. So we at work internally do something of that sort to solve the problems that you just mentioned, right? So we are going to open source that, so hopefully that would help.
Great, glad to hear that, and would love to see it when it's open source. Fantastic.
Sure. Thank you. Tiffany? Can we get the mic right down here? Thank you. Thanks, Tyler.
Out of curiosity, when I work with my teammates, occasionally they have a notebook and I have a notebook, and when we want to interact with each other, it was difficult. Is there like a tool that is available for us to, let's say I run a data and then I could rerun it on another notebook?
So I'd have to specifically kind of look at very precisely what you want to do, but there is one piece of new machinery that is now being developed. One of my postdocs here on campus is leading the development of that, and it's within the sphere of Jupyter Lab, which is basically the evolution of the user interface of the notebook that the person in the back mentioned. What we have is Google Drive support, so that if you have a notebook and you share it with someone via Google, then you can both work on it in real time, and you can have real-time collaboration, and actually not just in the notebook, but it's actually in the entire Jupyter Lab architecture, which means you can collaborate on a text file, on a markdown file, where you're running markdown with blocks of code. You can have a chat window. That chat window, you can type Jupyter inputs and markdown and drop them into cells. So that real-time collaboration architecture is now, it's still very much in alpha because Jupyter Lab itself is changing under the hood, but it works. It works, and hopefully it'll stabilize in the next few weeks, couple months.
That is very cool.
Yeah, it's something we've been waiting for a really long time. We know it has been a long time coming. It has proven to be really difficult technical work to do because we want to do it not just for the notebook, but we want to do it for the whole, as I said earlier in the kind of HTTP HTML analogy, this is a whole architecture, and in Jupyter Lab, all the pieces of that architecture are available as individual components. So this tries to enable real-time collaboration on the entire architecture. And it's a lot of work, but we're very excited about it.
That's great.
I'll be happy to talk to others during the break, and thanks again for your time and your
Fernando,
attention.
thanks so much.